For over a century, humanity's understanding of the solar system relied almost entirely on deep space optics. We learned about our neighborhood by looking through a lens. But observing from 93 million miles away creates a massive filter. Over that distance, the dynamic streams of solar wind smear together, hiding the precise origins of the star's energy. We hit a similar wall with the moon. The 238,000-mile gap between Earth and the lunar surface introduces a severe communication delay. That lag makes the remote control of precision robots sluggish, unpredictable, and highly hazardous. This distance locks us out of major scientific mysteries. We can't see exactly why the sun's outer atmosphere burns at 1,000,000 degrees when its surface is comparatively cooler. And we can't safely map the deep, permanently shadowed craters of the lunar South Pole. Passive observation has taken us as far as it can. To capture uncorrupted data and solve these problems, we have to physically close the gap. NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter were designed specifically to survive extreme heat and take in situ, or direct localized, measurements closer to a star than any previous spacecraft. Their target is the Alphen critical surface, a lumpy boundary where the sun's inner atmosphere stops spinning and solar wind accelerates into space. By flying inside this boundary, probes measure the plasma in its pristine, undisturbed state. This proximity immediately yielded answers. Instruments detected switchbacks, sudden magnetic kinks in the solar wind, and traced them straight down to funnel-shaped convection cells churning on the star's surface. They captured tiny, continuous solar eruptions, entirely invisible from Earth, providing a direct mechanism for how the corona is superheated to extreme temperatures. By physically touching the star's atmosphere, we are replacing decades of theoretical guessing with hard, actionable data about stellar physics. A similar operational shift is happening closer to home. Artemis aims to explore the unmapped, hazardous, permanently shadowed regions of the lunar South Pole. Instead of managing these surface missions entirely from Earth, NASA and its partners are building the Lunar Gateway, an orbiting deep space outpost that drastically cuts the physical distance between human operators and surface robots. The European Space Agency is already testing this proxy exploration model on the volcanic, lunar-like terrain of Mount Etna. In these trials, an astronaut situated in a simulated orbital environment teleoperates a surface rover. Operating from orbit effectively eliminates the time delay. This near-instant communication allows for true haptic force feedback, meaning the human can actually feel physical resistance. This zero-latency human-machine symbiosis projects our physical intuition directly into lethal environments, keeping astronauts safe while preserving the exact precision of human touch. The era of deep space exploration has moved past the optics of telescopes. We are now relying on physical presence. The pristine data collected from the sun has immediate survival applications. Tracking those energetic particles allows us to accurately predict dangerous space weather and coronal mass ejections. These solar storms are capable of causing acute radiation sickness in astronauts operating outside Earth's magnetic shield, and they can easily overwhelm high-tech power grids back on the ground. At the same time, mastering real-time telerobotics on the moon builds the exact infrastructure required for the future. These same techniques will be used to execute Mars sample returns and assemble permanent planetary bases. Getting dangerously close to our cosmic neighbors serves a distinct operational purpose. It is the gathering of vital intelligence required to survive in the vacuum outside our atmosphere. By charting our star's explosive physics and the moon's treacherous terrain, humanity lays the groundwork to safely expand outward into the solar system.